Good morning. My name is Brian Abraham Hernandez Caro, and I'm a student of material science at the University of Guadalajara. Today, I'm pleased to present this research entitled My Career in Electrochemical Analysis of Sintered Titanium Cerium Dioxide Composites for Potential Biomedical Purposes. Biomaterials can be defined as a material used to replace a part or function of the body in a safe, economical, and physiologically acceptable way. It is essential to keep in mind that when discussing biomaterials, the concept of biocompatibility must be taken into account. This term refers to the extent to which non-living materials are biologically acceptable to the tissues that come into contact with them. The types of biomaterials that can be used are classified into four types: polymers such as nylon, silicon, and polyester; metals such as titanium and its alloys and cobalt chromium alloys; ceramics such as alumina, calcium phosphates, and carbon; and finally, there are composite materials. Titanium matrix composites have increased their relevance in several areas of the industry, but with a special focus on the biomedical area. Reinforcements with ceramic particles generally manage to improve the mechanical properties of titanium without greatly affecting corrosion resistance and biocompatibility. Multiple studies have shown ceria to be a beneficial reinforcement for metal and titanium matrix composite systems, leading to notable enhancements in the mechanical properties of the composite. In addition, this material has demonstrated biocompatible properties and the capacity to regulate inflammation. In the majority of these studies, ceria has been utilized in coatings or in the form of nanoparticles. Consequently, there is a paucity of information regarding its influence using micrometer-sized particles. For this project, it was determined that different concentrations of ceria would be used, yielding 4 samples with concentrations of 0, 5, 10, and 15% by volume of ceria. These samples were manufactured using the powder metallurgy technique. The powders were then mixed, PPA was added as a binder, and they were compacted using a universal testing machine. The green samples were extracted from the device to proceed with their sintering in a furnace. The sintering process was carried out following isothermal ramps. First, the samples were heated at a rate of 10 degrees Celsius per minute, up to 500 degrees for 45 minutes. Then the samples were heated to 1300 degrees Celsius, where they were maintained for 60 minutes. Finally, the furnace was cooled slowly to extract the samples. The samples were characterized following metallographic preparation, employing silicon carbide sandpaper for roughing and alumina of 3, 1, and 0.05 micrometers, in addition to a 0.02 micrometer silica solution for polishing until a mirror finish was achieved. Initially, the samples were characterized by X-ray diffraction technique, followed by microstructural characterization through scanning and electron microscopy images. The characterization of the material's mechanical properties was conducted through a series of analytical procedures. Baker's microhardness tests were performed to ascertain the material's microhardness. Dry microwear tests were conducted to determine the material's friction coefficient and wear rate. Electrochemical potentiodynamic polarization tests were performed to evaluate the material's corrosion resistance. The results obtained were as follows. SEM images indicate the presence of an alpha equiXL titanium phase. As the ceria content increased, zones of lighter tonality were visualized, suggesting the presence of phases of the ceramic in the sintered materials. These phases are observed to be agglomerated in some areas, but also occupying grain and pore boundaries in the material with 5% ceria. In the samples with 10 and 15% ceria, it was observed that titanium particles did not fully coalesce in several zones. This was likely due to the ceria occupying the ground boundaries and pores. However, due to the amount of ceria used, ceramic particles were formed barriers between the metallic particles. It was determined that the sintering process was incomplete, remaining in the early phase of neck formation between the particles. These observations are based on the previously mentioned observations of the behavior of ceria in the microstructure and behavior of metallic particles during sintering. The results of XRT test aligned with the microstructure observed in the SEM images. The presence of titanium alpha phase is evident in all materials, and the phases of ceramic particles are discernible in the samples with ceria. The presence of peaks of cerium 4 oxide phase and cerium 3 oxide phase is observed, with the amount of the latter increasing as the ceria content in the material increases. This suggests that a phase transformation occurred in the ceria during the manufacturing process due to the high sintering temperatures. The micro-hardness test demonstrated a steady rise as the ceria content of the titanium increased. The primary factors contributing to the hardening effect in the composites are likely to the uniform distribution of ceria particles within the titanium matrix and the refinement of grains in the microstructure. The dry micro-wear test allowed us to determine the friction coefficient of each sample. In all cases, a rapid increase was observed in the initial stage of the contact between the alumina ball and the samples. After 2 minutes, the test stabilized due to the accommodation of the surface roughness. This adaptation to the shape of the contact decreases adhesion forces. The addition of ceria to the titanium matrix promoted a decrease in the friction coefficient, yielding the lowest values for the composites with 10 and 15% reinforcement. In the titanium 15 ceria composite, an increase of this parameter is observed starting at minute 9, likely due to the rise in ceria particles detached during contact, which acted as a third body and caused abrasive wear. Subsequently, the volume lost in each footprint was calculated using an optical profilometer. A Chart's equation was then used to calculate the wear rate. After obtaining the results for the 4 samples, it was determined that the trend is the same as that of the friction coefficient, with the wear rate decreasing as the ceria content in the samples increases. Finally, the wear tracks were analyzed by SEM images. In the titanium image, the footprint with the largest dimensions was observed, measuring approximately 100 micrometers in height. The footprint exhibited several areas of adhesive bonds with plastic deformation, dragging and accumulation of materials towards the end of the footprint. Additionally, groups were observed likely resulting from detachment of material or abrasion caused by its dragging during contact. In the case of titanium 5 ceria composite, the footprint height and the areas with adhesion and plastic deformation decreased due to its greater hardness compared to the matrix. In the case of the materials with 10 and 15% reinforcement, the dimension of the traces continue to decrease, and even they are not well defined due to the fact that the areas where ceria is present apparently suffer minimal wear. Additionally, the presence of fewer zones exhibiting adhesion and plastic deformation is notable, along with the observation of isolated groups likely resulting from detached ceria particles during the sliding process. A preliminary analysis of the potential dynamic polarization curves indicates that the addition of ceria to titanium reduces the corrosion resistance of the composite compared to the pure titanium sample. These observations are corroborated by the parameters calculated and summarized in Table 2. As the percentage of reinforcement in the material increases, the current density increases by an order of magnitude, which decreases the corrosion resistance. However, the decrease is not critical, and its values are in an acceptable range for biomedical applications. What can be concluded based on the results? Mm, Titanium ceria composites were successfully fabricated by sintering under vacuum atmosphere at 1300 degrees Celsius for 2 hours. SEM images show an alpha ekixial microstructure, and the cerium oxide filled the spaces between titanium particles. Um, the alpha titanium phase was detected in all materials, and the cerium 4 oxide and cerium 3 oxide phases were identified in samples with 5% or more ceria content. The intensity of cerium 3 oxide phase peaks increased in materials with 10% and 15% ceramic particle content. The micro hardness increased with the addition of ceria to the titanium matrix, while the coefficient of friction decreased slightly. The titanium 15 ceria composite is 43% harder than unreinforced titanium. Combined adhesion and erosion mechanisms were observed in the wear tracks. It's likely that ceramic particles detached from the samples act as a third body in the contact. The dimensions of the wear tracks were smaller in the materials with ceria particles. Consequently, the wear rate diminished as the particle content in the materials increased, enhancing wear resistance. As the percentage of ceria increased, there was a gradual decrease in corrosion resistance. However, this decrease was not critical, as the values obtained can be considered acceptable for potential biomedical applications. According to the results of the test, the composite material with up to 5% ceria particles shows great promise as a viable implant material. Its mechanical properties demonstrate significant improvement compared to the pure titanium, and while its corrosion resistance is slightly lower, it remains within acceptable limits for biomedical applications. And that's all. Thank you very much for your attention.